You're on.
All right, well, welcome everybody. Today, we're going to be going over some stuff on transmission line protection. I'm Brandon Davies, and I'm going to be doing the next 5 classes, including this one, 4 on transmission line protection, and then the 5th class on bus protection. So,
Brandon, I forgot to mention too, they did just had a test where I asked them to configure protection for if you left the ground lines out on a line. If you can explain a little bit about protection, because that was a struggle for some of the folks. So maybe at some point, if you haven't done that already, you can include that in.
Okay, yeah, I could probably work that in there. So yeah, today really I'm going to do overview. In the next couple classes, we'll go into a little bit more detail on a few different line protection schemes. So a little bit of an agenda for what I'm hoping to cover today. I have not gone through and done a draft run on my presentation, so I have no idea if it's going to take me 20 minutes or 2 hours. So we'll see where we go. But I'd like to keep it pretty open. If anyone has any questions as I'm going, definitely, virtually raise your hand or just come off on mute and get my attention so that you can get the question out there. So for the agenda for today, really going to start out with introduction about myself and my background, and a little bit about my career path and work that I've done over the years. We'll take a look at transmission lines and kind of, how they act in the power system, what they're there for, what are physical characteristics, electrical characteristics, take a look at the types of things we need to consider when looking at faults on the transmission system, or in particular on transmission lines. And then we'll start getting into some of the fun protection stuff towards the end of the class today, going over high-level protection system objectives, which is probably some duplication of some of the stuff you've covered already with some of the other presenters throughout the semester. And we'll take a very high-level look at transmission line protection and what type of protection elements we'll be using and learning about over the next few days or a few classes. And then kind of wrap it up with some Q&A roundtable. But again, if you've got any questions throughout the presentation here today, definitely jump right in. Let me know. We can dive into detail on any topic that that you want to related to the scope of what we're going over today. So for introductions, a little while ago, they had me work up a career path document for something. So I thought I'd include that in here. Go over a little bit about myself. So I graduated from the University of Maine EET program back in 2006. I shortly after that started working for TRC Engineering, which was ePro back then. And came into the group as a protection and control engineer. Really, coming out of the ET program, I didn't really have, I understood what protection was, but we didn't have this advanced class, so I didn't have as much of an opportunity to learn more about protection ahead of it. So I was just really excited to get into some real engineering work in my first job. And I spent the first chunk of my career really diving into the details and learning a lot about protection systems. I really started out in a more of a PNC design capacity, working primarily with developing drawing packages, your relay one lines, schematic diagrams, wiring diagrams, which I think you learned about a little bit earlier in the semester. And I did that for several years. Shortly, a couple years into my career, I decided to start doing an online master's program through Michigan Tech. And I worked on that for several years as part of the TRC tuition reimbursement program. So they covered that, which was really nice of them. And I eventually finished that program in 2012. Around that same time, got my professional engineering license. Shortly after that, there was a decision made to kind of split the protection team at TRC into folks more focused on the design drawing aspects of the work and another group that was more focused on the settings side of things. I shifted over to the one more focused on fall studies and settings. And I did that for several years in a capacity of developing, reviewing, leading settings projects for a variety of utility customers across the country. Until 2017, when I decided to take a try at a supervisory position. So I became a supervisor of our team based in Augusta, Maine. And I was in that role for quite a while until 2020, when I eventually decided to take on a little bit more of that responsibility and took over as manager of both the protection group and the automation and integration team. And a couple of years ago, they decided to break off everybody nationally who does the type of work that my team does and put them in a technically focused group. And I'm now running that team of just under 60 engineers nationally and in Canada that are very technically focused in relay settings and automation type work. So that's what I'm currently doing today. I still stay pretty technically engaged, both with some project work here and there, and also with some of my involvement with the IEEE, which I continue to be very actively engaged in the IEEE Power System Relay Committee, Relay and Control Committee. That's the group that writes, updates, maintains standards related to protection and control type topics. So a lot of the stuff you'd reference as a protection engineer is either papers written by the PSRC or standards documents, guide to transformer protection or transmission line protection. That's the type of stuff that the team does. And I'm currently the vice chair of the IEEE PSRC K subcommittee, which deals with substation equipment protection. Been really engaged in protection work pretty heavily for the last just about going on 17 years now. So I've had a lot of opportunity to see a lot of different stuff, and I'm hopefully we'll be able to kind of pass some of that along to you through this presentation. If you got any questions on stuff, like I said, definitely stop me and ask the question. I'm happy to talk about kind of any topic, protection related topic, as we kind of move through the presentation today and over the next couple of weeks. So I won't necessarily do introductions for the folks that are on here, but I would be interested out of the folks who are online right now for students, how many of you are going to be working in the kind of utility power space, and if any of you are going into protection related roles come graduation this spring.
My name's Shannon Scott. I'm actually working currently part-time at a series of hydropower plants, and definitely going to be working with the relay equipment there.
Oh, great. Excellent. Yeah, a lot of interesting stuff, a lot of real need for folks getting familiar with rotating machines these days. Out of all the disciplines at the PSRC, I know it seems like the rotating machine stuff is a very unique specialty that I'm sure you'll find a lot of use for gaining that experience earlier in your career here, because there's a lot of rotating machines out there, and I think less and less folks over time who really know how they work. So that sounds great. I guess anyone else?
Hey, Brandon. My name is Ben Brooks, and I'm currently working part-time at Central Maine Power in the distribution planning group there.
Oh, excellent. Yeah, distribution is another area that's really blowing up with the amount of change going on in the distribution system. So yeah, I'm sure really across the board, any power related job is got a lot of kind of interesting stuff going on. But I know we're doing a ton of work in the distribution system these days, just because there's such a push to kind of modernize that part of the system now that a lot of the transmission system has had an opportunity to get have some work done to it. I guess anyone else? All right, well, we'll move on from here. Really nice getting to know all of you, and look forward to working with you over the next few classes here. So I work for TRC. I'm located in Brunswick. I'm at my home office. You can probably tell I'm not in a cubicle here. I work primarily from home, though we've got an office in Augusta that that several folks do still report to, and we're in the works on relocating a second office down in the Portland area that will be getting started. But we're a large national company, slightly international, I'd say, with offices throughout the country. And really, we serve utility customers, generation customers, municipal co-ops, generation facilities, renewables developers, and owner operators. Really, any kind of anything having to do with the power system, we've really got a lot of expertise there. Our team is a small piece of it, but really past that, anything that a utility could look to have done, chances are we've got somebody with some experience with it. And we serve customers really or across the country. We do a little bit of work outside of the US, but not a lot. Really, the larger investor-owned utilities throughout the US are really our core target clients, and then really have been moving in a lot more into the renewables market in the last 5 years or so. So we've got about 7,000 employees, 150 offices that work both in the power sector, but plus we've got an environmental wing, a infrastructure group that does kind of non-power infrastructure type projects, and then a digital group that does a lot of kind of advanced digital solutions for dealing with large amounts of data and developing custom programs and tools for our clients across all the different practices. So that's a little bit about TRC, and we can kind of move from here into some of the technical content of the day. So, as I mentioned, we're gonna be talking about transmission line protection over the next several classes, and really want to use this first one to provide some kind of basis and background on the transmission system. Really, the transmission lines are one of the key components of how our electrical grid operates. We need to get the power from generating facilities to distribution substations to be distributed to customers, and that's done, primarily with AC transmission lines. So typically, I think you just did some a few classes on distribution protection and probably learned a little bit about the distribution system. So generally, the cutoff for a transmission, an AC transmission system, it's usually pretty much always a three-phase AC type system. Operating voltages range from about 69 kV up to 765 kV. Anything under 69 kV is either considered sub-transmission or distribution. I've heard a utility call it transmutation before, but really once you get below 69 kV, you're no longer really trying to move a large amount of power around. You're really distributing it to the folks who, the different customers that would be using that power. So really we're talking about the high voltage lines rather than the distribution lines that you would see following the roadway while you're driving down the road. Anything above 100 kV is generally considered part of the bulk electric system. So when we're talking about transmission system, that's another way to look at it, is that 100 kV cutoff. And there's some compliance requirements and other things that come into play once you hit that 100 kV mark, that you have to do certain things, and you have to comply with certain requirements that are put out by NERC and other regulatory bodies. So AC transmission can be either overhead or underground, or under the water. You can have underwater cables, and hybrid variety, including both. So you might have an overhead section and an underground section. I don't have a specific statistic, but I would say that almost all of our transmission system is overhead, just based on the high cost of doing underground transmission lines. It does get very expensive to transmit the same amount of power underground compared to overhead. So generally we're talking about overhead lines, though a lot of the similar types of protection schemes and considerations can be applied to underground or cable type transmission. So when we're talking about a transmission line itself, there's obviously the conductors, the towers. I've got this picture here on the slide deck that shows a transmission line with a transmission tower on it. It's actually two lines because it's a double circuit configuration. But that line has to go somewhere. And so generally when we're talking about a transmission line, the ends of the transmission line are going to terminate at switching devices at a substation or a switching station. So it would come from one station, and you typically have a breaker that would be used to switch the line on and off at each end. And that'd be your switching equipment. And that's really the boundary of what we call a line. On the other side of the breaker, you consider that bus work or a transformer or whatever you're terminating into on that other side. And again, the primary function of transmission lines is to transmit power between generation and utility substations, and eventually move that power down to the distribution so that it actually can go out to customers. So a lot of the transmission power lines in Maine, especially at 345, are primarily moving power from north to south to feed the larger kind of load centers in the rest of New England. So that's generally, if you think about the main system, that's the larger transmission lines you're seeing. That's largely what they're doing, is moving them across. So if we look at kind of a simplified view of the power system here, and this is very much oversimplified, but really we've got generation. This is where our power is coming from. It could be wind or solar. It could be hydro facilities, nuclear facilities. And that is generated at a given voltage and stepped up through a step-up transformer to connect into the transmission system. In some cases, it also connects in the sub-transmission system, or more and more we're seeing distribution connected generation these days. But it would generally step up, and the larger generating stations are going to be stepping up and connecting to the transmission system, where they can sell their power onto the grid, and the utilities move it from the generating site through the transmission line down to another substation. This would be a transmission to distribution type station, where it would step down to a lower voltage and would go across the lower voltage distribution lines to get out to houses, businesses, industrial customers, things like that. There are some cases where you've got larger industrial facilities that have high power demands that would connect directly into the transmission system. But largely most of the customers to a utility are connecting it in that sub-transmission or distribution type level. So, as I said, this is a very overly simplified view of the power system here. It really shows a single line moving all the power from the generators down to a single distribution circuit here. The reality of it is it's a much more complex system. So if we take a look, this is a very zoomed out view of the ISO New England Aspen model. And this is Maine. So you can see here, it's obviously very hard to read and see what it is, but all of these kind of pink colored lines here are representing our 345 kV system coming from northern Maine through Maine and eventually heading out down here towards New Hampshire. All the red lines represent 115 kV transmission infrastructure. So, it's a lot less linear than the simplified depiction of it, and it's really a large grid of connected transmission lines that make up the bulk power system, the bulk electric system. So if we take a look at the physical characteristics of a transmission line, it's really made up of a handful of components that are kind of important for us to understand as protection engineers, because we have to understand the different failure modes of those components and how the types of faults, the types of failures we would need to detect as a protection engineer. So really the main components of a transmission line are the transmission structure itself. So we've got to have something to support the lines and keep them suspended and up off the ground. We've got insulators, which provide a connection point between the transmission structure and the conductors. And then we have different conductors. So typically, again, we'll have a three-phase power that we'll be transmitting. So we'll have phase conductors and then ground conductors. The ground conductors are oftentimes located above the phase conductors on the structure, and that provides a path for lightning strikes and things like that to happen. So on the right-hand side here, I've got a couple images of what these conductors look like. So the most common type of conductor that typically we would see is for the phase conductors or for ground conductors as well. Is aluminum conductor steel reinforced. So it's ASCR. I think I messed up that acronym, but that's all right. But basically, it's a steel strands in the center of the conductor, and those are really there to provide the structural integrity of it. There's a lot of forces. There's a lot of stress on these conductors because they're spanning large distances and they have a lot of weight. They need to handle wind loads, ice loads, things like that. And then aluminum strands that go on the outside of that are the primary path for your current to flow through the conductors. The other type that I have here is an optical ground wire. So this is becoming more and more common for the ground conductors on the transmission structure to provide a conductor that has the same aluminum strands on the outside, some reinforcing on the inside, and then in the center or a portion of the cable is actually filled with fiber optic strands. So this allows you to, when they're rebuilding a transmission line, to also, build a communications network to allow for connectivity to the substations use in protection schemes that require communications that we'll talk about in a couple classes, and other uses. They can lease out and sell the use of these fibers to other telecommunication and other types of companies as well. So the transmission line design itself has a huge amount of engineering that goes into it. It's, I'd say, primarily a civil engineering, structural engineering type of exercise, because you're really looking at the, designing the towers and the conductors to deal with all the different stresses and loads that are going on due to the conductors, due to weather, while maintaining, appropriate conductor spacing. So there's a ton of stuff that goes into it, and I'm not a transmission engineer, so I can't tell you all the details. But some of the key things are really the load capabilities of the structure, the conductor spacing. So you need to keep your phases separated from one another. The conductor sag, which is how far the conductor will move, will go down when at different temperatures. The tensions on the conductors, which have a lot to do with the design of the structures themselves. Clearances, so you're working with very high voltage equipment, so you really need to maintain appropriate clearances with anything that the conductors may come in contact with to prevent faults. And then finally, wind and ice loading. So you're going to need to design this thing to operate in all weather scenarios and things like that. And certainly extreme weather events are seemingly more common these days. So that's being a bigger and bigger concern in how they design these transmission structures and the transmission lines themselves. So I've got a cross section here of some different transmission type structures. These are all 115 kV transmission structures with different arrangements. And you can see here you've got, each one has all of those components. It's got the structure itself. It's got insulators for hanging the conductors. It's got 3 phase conductors coming off the insulators. So you've got ground conductors that are connected in various locations, and they come in different configurations. So depending on the needs of the project and things like that, they would select different types of structures. But this is probably some of the types you'd be likely to see, on road crossings and things like that. The one on the right here is set up so you can actually use this same structure for 2 separate lines. So you can hang one off of one side of the structure and another off of the other side of the structure. So that's a double circuit configuration. It's fairly commonly used if you've got parallel lines that are following the same path for a longer distance. So that kind of explains how the physical characteristics of the transmission line, the transmission structures. So the next thing we can really take a look at from that is the electrical characteristics of the line. So there's a couple things as protection engineers we're going to look at and we're going to be concerned with the transmission's impedance. So obviously we need to understand the transmission line impedance to do our fault analysis, because that'll drive our system modeling parameters that we enter into Aspen or some other modeling software. It's going to be an input to some of the protection calculations that we'll work through. And so it's important that we get an accurate model of what this electrical characteristics of the line are going to look like. So when we go to take a look at a transmission line and determine what its impedance is for use in studies and different types of modeling software, we got to look at a number of things, because it's not quite as straightforward as you've got a conductor up there and it's got an electrical property, and you can probably look up a cut sheet and find a resistance value for that conductor and be done with it. And it's not that simple, because there's a lot of other things going on with a transmission line. So certainly the conductor itself, conductor's impedance itself, is a big piece of the electrical calculation of a transmission line's impedance. That's going to include the resistance of the conductors. So we've got aluminum conductors going for a certain distance. We can look up, the physical parameters for aluminum. We know how much the cross section is. You can go from there and calculate the resistance. But there's also going to be an inductance piece of it due to the internal flux within the conductor itself. So there's an inductance aspect to the conductor impedance that's determined by the type of conductor. Some of the other stuff we've got to consider when coming up with a transmission line impedance is the interaction between the conductors themselves and the interaction between the conductors and ground. So there will be a inductance that's shared between the conductors due to the flux linkage. You've got energized conductors up here running in parallel. So there is going to be an amount of inductance from phase to phase, or in the case of a circuit like this, each phase would kind of have its pair of how it's interacts with the other and couples to the other phases. And there's going to be capacitance as well. We've got two energized conductors that are out of phase with each other. So there'll be a capacitance both between the phases themselves and between the phases and ground that need to be built into the calculation of those parameters. And then if in the case of what I showed on the previous slide, where you've got multiple lines sharing the same space, so sharing a right of way, one of those clear cuts through over a patch of land, there'll be a mutual impedance between the different lines as well, because you may have current flowing on one line that then shows up on another line because of the flux linkage between the conductors on one transmission structure and another transmission structure, or if it's a double circuit kind of configuration. And really that mutual impedance comes into play heavily when we're doing transmission line fault analysis. Normal load flow does have an impact, but the magnitudes of the currents are lower. So the impact of that, the mutual impedance that's shared between the lines is lower. When you have a fault and a higher current, more of that current can couple over to the other lines and can impact how, the operate quantities that your transmission line relaying and other system relaying in the area will see. So that needs to be accurately modeled so we can understand those effects and account for those in the modeling that we would do. So you can go through the process of calculating all of these impacts by hand. I wouldn't recommend it, but you can do it. But what we do, as we do for pretty much everything as practicing engineers, is we leverage specialized software to do that. So there's a number of different softwares out there that basically you can map out the conductor spacing, the height off the ground, spacing between phase conductors, where the ground conductors are located, the types of conductors, and full of other parameters, and it will go through and do all the math for you and come out with a result that will say, for this type of structure and this type of arrangement with these types of conductors, here's your positive sequence, zero sequence, negative sequence impedance for for this line per unit length. So it might come out and say we've got a certain amount of R plus JX for a positive sequence, and and that's per mile. So if you got a 15-mile long line, you can go through and do the math and come up with the electrical parameters. That software will also do the same thing to evaluate the mutual impacts of other lines. So if we were in a corridor where we had 4 or 5 lines, it can go in and determine what the mutual impedance impacts are between one line and another. And that's one of the things that, you know, we would take and enter into our fault model, like the Aspen or CAPE or some other software to accurately model how the system is going to respond to different conditions. So, you know, usually what we're going to get out of a software like this, and there's a bunch of different ways you can model transmission lines with different approaches, with different level of details that you use for different types of studies. But as protection engineers, generally, you know, we're not using anything other than the pi equivalent model that I've got shown here. And this basically takes, it's a fairly simple approximation of a transmission line. You know, it breaks the transmission line down into, you know, your impedance here. That's the transmission line's impedance itself. So you've got, you know, your R plus JX value here. And then it'll take that capacitive, the shunt capacitive impact of the conductors, you know, over the length, you know, their interaction with ground, and it will take, you know, half of that susceptance, and it's going to put it at one side of the line terminal, and it's going to put the other half at the other line. So this isn't 100% accurate to what's really going on, because this capacitive effect, the shunt capacitive effect or susceptance effect, is actually distributed throughout the entire transmission line. And you know, it's not lumped as it is on here, but for the purposes of a protection engineer, yeah, this model is more than enough. And in fact, for most protection applications, we are ignoring the capacitive effects, because the impacts of charging capacitance on the line are negligible compared to the, you know, the other values that we would be looking at when we're talking about fault magnitude. So we can completely ignore this as well. So generally, we're really just focused on the, you know, positive sequence and zero sequence impedance values that are in series here. So, you know, we can then take that transmission line electrical model, pi equivalent model, and look at it as it relates to the rest of the system. So probably the simplest approach to that is to take the Thevenin equivalent of the system on one side of a transmission line and the Thevenin equivalent of the system on the other side of the transmission line. And we can make this very, very simple system equivalent. So your Thevenin equivalent here, you've got your voltage source and your receiving end equivalent impedance. We've got our line impedance, and then we've got the sending end voltage source and impedance. And you know, in reality, if you do a Thevenin equivalent of a very complex system, you'll probably have a transfer impedance. You'll probably have some other stuff going on that would need to be accounted for on it. But when we're really just zooming in on this line impedance, that's usually good enough for discussion purposes. And oftentimes, this type of figure will be what you'll see if you you know, look in technical papers or guides and things like that about transmission system, because it's easy. It breaks it down into some fairly simple parameters. So I guess any questions on the transmission line physical or electrical characteristics before we start talking about faults, or anything I've covered or anything related to what I've covered?
Brandon, can you just maybe really quickly, when you talked about mutuals, can you talk about just briefly, like more of an issue with grounds than it is for phase?
Yeah, so the you know the mutual coupling is a much bigger issue for your ground ground faults and ground protection. And so it's typically we're looking at the zero sequence mutual coupling. There, we really don't have to consider coupling for the phase or positive sequence quantities. You're testing my memory here, Paul. I believe it has to do with the fact that the balance quantities kind of cancel each other, the impacts out, where for a zero sequence path, you aren't balanced anymore. So that coupling has a bigger impact. Am I on the right path there, Paul?
Yes, I believe that that's the case. Yeah.
Okay. But yeah, so really when we're looking at the mutual coupling impacts, the output of it's going to tell you, all the parameters, but it's generally the zero sequence mutual coupling that as protection engineers, we're the most concerned with, because it's going to have the biggest impact on our protection. Good question, Paul. Anyone else have any other questions on what I've covered, or how we go about doing any of that analysis I've talked about so far for the electrical piece of it?
Just a quick question. Do you mind going over insulators again?
Yeah, no problem. So let's see if I can back up a couple of slides here. So your transmission structures here, they're a very convenient path to ground for your fault current. So on any of your transmission structures, you're going to have something to separate the structure itself, which is that path to ground, from the energized conductors. So usually what you'll see is these bell style insulators that will be hanging off the structure itself. They're set up that way so that water drips off of them and down, and doesn't create a continuous path of water across the insulator that you could arc over. In general, you're going to see more of these insulators the higher the voltage that you are working on. So this is a 115 kV line, and there's probably a typical metric of, you need X amount of insulators per kV, or for a certain amount of kVs would cover a single insulator. But in general, we've got 6 or 7 of those insulators stacked on each other for a 115 kV, and that's designed and engineered in a way that prevents the electrical path from happening between your energized 115 kV conductor and the ground here, because you're going to have it's 115 kV line to line, so you're going to have 60 to 70 kV voltage difference between these 2 points, and that insulator prevents a electrical path from happening between the energized conductor and the structure itself. Is that in line with what you're looking for some additional?
Yeah, just sort of some background on it. Yeah, thank you.
Yeah. So you'll see these, and there's a bunch of different types of arrangements and stuff, but in general, any of those transmission structures like this, they're all going to have some type of an insulator here. So these ones are kind of suspended off of the line. These ones are physically mounted off the sides. I'm not an insulator expert by any means, so I'm sure there's a lot of stuff that goes into specifying and selecting transmission line insulators for various applications. But in general, that's really what they're there for, is to prevent an electrical path from the conductor to the tower itself, which would be a fault. So any other questions before we move on? All right, awesome. Okay, so now we've covered kind of like what is a transmission line, how is it built, what what it's there for, and how it operates electrically. Really what we're concerned about as protection engineers is how can this thing fail? What can cause a fault? What can, what types of things do we need to provision our protection system for to isolate and fix a problem on the transmission system? So I'm sure in one of the previous, or probably all of them, they went over the different types of faults. So, we can be talking about a three-phase fault involving all three phases or three phases and ground. A single phase to ground fault, which is the most common type of fault. So one of the phases finding a path, some mechanism to ground. A fault between two phases or between two phases and ground is really what we're looking at here. And there can be a lot of different ways that can happen. There's a lot of potential causes for transmission line faults in particular. I looked for but couldn't find any metrics on frequency of faults on transmission lines versus other bulk power like substation equipment. My gut understanding is that there's a lot more faults on the transmission line itself than there are within the substation, but I just couldn't find any specific study or data to back that up to give you a good figure on it. But it makes sense because the transmission line itself is covering a huge distance. It's very physically large, which is going to then have a larger likelihood of having a problem. It's got more components in it because every one of those towers has insulators and jumpers and things like that. And it's not in as much of a controlled environment. There's a lot of stuff that we can do as engineers to protect a substation, a piece of substation equipment from things like lightning or animal contact, physical contact from trees and things like that. Within the substation fence, we can design around those things that, you're probably not going to allow a tree to grow inside your substation. You're going to have controls on vehicles and how they move around in the fence. You can put in some animal deterrents, things like that, where the transmission system doesn't have that. You can go and walk around underneath the transmission line, or trees can grow underneath it, things like that need to be maintained, but it's a less controlled environment. It's still controlled to some aspect, but not as much, which means there's a higher likelihood of a fault occurring on it. So some of the causes of transmission line faults is lightning. So lightning strikes is a big one. Obviously, you get a lot of big metal or wood or grounded towers that are crossing a clear-cut area. So lightning strikes are a big possibility and happen frequently on the transmission system. You can have wind. So again, you've got conductors that are designed to maintain a certain amount of spacing. But I know I've heard very many times about high winds and inconsistent winds blowing in different directions, causing the conductors to swing and eventually arc over. Ice and fire are another couple. So ice could load down the conductors to the point they break and make contact with the ground. Ash and soot from a fire and the smoke could cause a path for a arc to happen across from an energized conductor to another conductor or to ground. You can have equipment failures. So as insulators we were talking about, they've got a certain age, they've got a certain life, they get inspected, but they still can fail and do fail. And you can have a failure of that. Animal contact's a little bit less of an issue at transmission, just because the size of the and spacing of the transmission conductors are are much larger than distribution lines, where animal contact's a lot bigger deal. But you could have a very large animal or bird or something perch up on a transmission structure and potentially be enough to cause a fault across it. And then physical contacts. This could be trees, vehicles, hitting poles, things like that. And again, that's a little bit less of an issue for transmission system than it is for distribution system, because your transmission lines aren't generally following the roadside, so you're going to be a lot less likely to have a car or truck hit the pole and cause damage. They're also a lot larger, so even if a truck did hit it, it may or may not fail. And trees and other vegetation, it's a fairly controlled environment. Utilities do vegetation management for both transmission and distribution systems, but really, there's only so much trimming of trees you can do on the distribution system compared to the transmission right away is pretty much clear cut underneath, and they go through every certain amount of years and inspect and trim it down to prevent a tree from growing up underneath. So those are just some of the possible types of causes for transmission line faults. I'm sure there's a lot others out there, but those are the main ones that I'd say are probably the most likely scenarios that would come up. Okay, so now that we know that faults can happen, what's unique about transmission lines and what drives the fault response, the electrical fault response for a transmission line? So one of the things we have with the transmission system is we have variable fault locations. So, this ZL here represents an impedance. This might be distributed over tens or even 100 or more miles. And the fault can happen anywhere on it. So if a fault is close in, you're going to have a different fault response than if it's halfway through the line or towards the remote end of a line. And as protection engineers, we need to provide a protection scheme that will cover all of those possible scenarios, all the fault types, all possible fault locations. And we also need to consider the system impacts as well. So system configuration is going to have a big impact on the fault magnitudes that we'd see for a given fault. If you had a fault halfway through a transmission line, and then you have the same fault a week later, but you'd switch generation out or switch transmission lines out for maintenance, or the system was otherwise different, you're going to have a different Thevenin equivalent behind here, and you're going to have a different fault response. So we're really going to have to look at all the possibilities of what could be going on in the system and make sure we're covering any reasonable consideration that we would need to do there. And then finally, evolving faults. You can have a fault that starts out as a certain type of fault and then evolves into another fault. So it starts out as a single line to ground fault and then eventually turns into a phase to ground or a three-phase fault. And then lastly, you might have faults that are transient versus permanent. So if you have a lightning strike and you flash over an insulator due to the lightning strike, once the protection clears that, all of your equipment is still fine. The lightning strike is gone, and you can re-energize your system, and that's considered a transient fault. Another fault like a down conductor or a tree coming in contact or an insulator failing would be a more permanent fault that you'd have to go out and do some maintenance to correct that. So I've got a quick video here for the play of a transmission fault here. That's an evolving fault. So you can see here it's involving flashing over and arcing across one of the phases. And that arc eventually works its way up to another phase. And then finally the third phase. Changes from the start inception of the fault to the, to the final configuration of the fault. So I can tell you as a protection engineer, this is not, move away from that. That is not how we want our protection system to operate. That fault should clear in well less than a cycle. It should be, or less than a second. Should be a matter of cycles for that fault to clear. The fact that someone had enough time to get their phone out, start recording, and then watch it as it goes through that whole thing tells me that it was a pretty big failure of the protection system. So, that's what we're trying to avoid as protection engineers, is situations like that, because obviously it's going to cause more equipment failure. It's potentially dangerous for people that are in that area. And it's going to cause a much bigger issue to the system overall. So I think I'm definitely going longer on my slides than I anticipated, but we'll pick up the rest of them tomorrow. So, or on Tuesday rather. So I've got a few slides here with some questions just to kind of think about how the system's going to respond to a fault. If we have a three-phase fault on this bus in this location here, and we've got a relay located at the terminal of the line near the the bus S over here. What is the electrical system or electrical parameters measurements that relay is going to be doing? What are they going to look like during the fault? So, what's going to happen to the voltage and what's going to happen to the current? And from that, what does the impedance look like? I don't know if anyone wants to venture a guess on any of those questions. I've got enough for everybody. So, if someone wants to pick this one as the easy one.
I would guess the voltage is going to drop.
Yeah. Yeah. And that's the case. Your voltage is going to drop because you've grounded out, or you've shorted out your system here, which is now going to have a voltage drop. That's going to be a voltage measurement at the bus. It's going to be, determined based on a voltage divider between the source impedance and the line impedance. How about the current?
It's going to go up.
Yeah.
Oh, sorry, Ben.
All right.
No, you're good.
That's right. The voltage will go down and this current's going to go up, which is a handy thing for us protection engineers, because those are some quantities we can take a look at. How about the impedance? So if we're measuring voltage and current at this bus S, we can turn that into an impedance measurement. What impedance is that relay going to see for this fault case?
High impedance.
Well, this was the hard one out of these three questions. I've got a couple more slides with questions as well. So basically, the relay is going to see this ZL quantity because you're looking at the current through ZL, and you're looking at the voltage across ZL. So it's going to basically, the relay is going to see that line impedance. So that would be the measured impedance. So it's another operate quantity we'll talk about that we would use as a relay engineer to protect that line and detect that fault. All right, so we get a couple more slides with other questions. Assuming everything else is equal and you have two different faults on the same line, and again, we're looking at a relay quantity or a relay measurement at bus S here, the bus S terminal of the line. Which fault location is going to have the higher fault current, fault 1 or fault 2.
Fault 2.
Well, thank you for venturing a guess out there. So if you think about it as an electrical circuit, we've got a voltage and we've got impedance. So if you have fault 1, your current's going to be solely driven on this voltage and this impedance. And at fault 2, we're going to have both ZS and ZL in between the source and the fault. So the fault 1 is going to see a higher current, just because it's got a lower impedance between the Thevenin equivalent voltage source and the fault. And fault 2 will see a lower current. Those types of things are just kind of, I put these questions in here, not anticipating, not trying to put you guys on the spot here, but really just want to get thinking about these different things. What's going to happen during faults in these different locations, because it becomes very important concepts to understand as a protection engineer. You can go into Aspen or other software and it'll give you the answer, but understanding conceptually how the system's going to respond is an important thing to be able to validate the results that you're seeing and say, does this make sense? So the last one's another kind of tough one conceptually. So if we've got that same fault 1 location, so it's somewhere near this terminal, but we have we have one of the many branches of the transmission system that makes up this CS, and we take it out of service. So we open it, we isolate it on both ends. It's no longer a path for current, load current or fault current to flow. What's going to happen to the ZS? And this is kind of an important concept when you start talking about system outages and other considerations. Anyone want to venture a guess on this? If not, I can give you the answer on this one. So, go ahead.
Sorry, wouldn't the total impedance decrease because you're disconnecting it?
Well, it's a parallel path. So if you vision this ZS as 3 or 4 parallel impedances, and you take one out, your impedance, the equivalent impedance, is actually going to go up because you removed a parallel path that would otherwise be included in this ZS. So when you take out a line out behind a relay or a transformer or a generator or anything else, in general, the response of the systems is the system is going to get weaker. So you're increasing your source impedance, which is going to then impact your fault magnitude. So as protection engineers, we look at, and we're looking at this fault, we want to see what happens with this fault, not only when the system's in its normal configuration, but when there's also a reasonable outage, a piece of equipment out of the system behind it, so that we can see kind of a high and a low range of expected values for that fault location or for that line. So, in this case, if you take a piece of the system out behind it, your source impedance goes up, and because your impedance goes up, your fault current goes down. So, as you work more with really any protection system, especially transmission lines where there's a lot of variability in locations and things like that, kind of getting some of these concepts and understanding at a broad level how the system's going to respond to different different types of changes is important. So, all right, that's my last of the questions for the group portion of things. So, I know we've got. Does the class run until 6:15 or is it 6:10? What time do we wrap up?
6:15.
Okay. Well, I'll cover a few more slides here, and then we'll pick up with the rest of the slides on Tuesday, and then we'll get into some of the other stuff. I made 3 slide decks, and I think based on the pace I've gone through on this one, that'll probably be enough for 4 days, maybe, and then some. So now that we've kind of covered a little bit about the fault response for different types of faults, locations, considerations for transmission line faults, the next thing we want to start thinking about as protection engineers is how are we going to respond to those faults? So typically we're going to have on each terminal of a transmission line, we're going to have a relay, or more commonly these days, redundant sets of relays. So, 2 dedicated relays on each terminal that would be operating in parallel with each other. And those relays need to be configured to detect the fault conditions and take action to isolate the line in the case of a failure. So generally that action is going to be monitoring, current, voltage, calculated impedances, other electrical quantities to say, is this a normal operation mode or is this a fault operation? And if it's a fault, you need to take some action to isolate that. You probably looked at trip circuits and things like that when you went over some of the PNC design drawing stuff earlier in the semester. But generally this relay is going to then take an action to trip a breaker or a couple breakers at the station and open up those breakers or trip the breakers to isolate the faulted part of the system from the rest of the system. So you generally have relays at both terminals. They're both doing the same thing, looking at the same fault. They're seeing different quantities because the system equivalent behind those relays at station A and station D are different, but they'll be configured independently to operate and trip the line off, both terminals of the line or all terminals of the line off in the case of a fault condition. So, this used to be accomplished with a whole lot of relays. We have a lot of very single purpose relays, but these days modern relays, probably the ones that you've worked with in the lab and things like that, are more advanced and have dozens of protection functions and dozens of protection elements within those functions that you can use as a protection engineer to provide the protection you need for the transmission line and detect all those different types of the failures in different operating scenarios and in different system configurations and fault locations and all of that. So when you look at a line relay, so it's a Schweitzer 421 transmission line relay, which is a very commonly applied relay, it's got a whole lot of stuff in it. But generally, we're going to pick and choose what we need for that specific application. And generally, on transmission lines, we're going to be looking at distance relaying, which uses impedance as an operate quantity. And we're going to be looking at directional ground overcurrent protection as well. So we'd be monitoring impedance and current as methods of telling if there's a fault or not a fault, and we would be using relay logic to then close contacts and operate the breakers to clear the fault. So though there is a lot of stuff in here, usually we turn most of it off and we only pick the things that we need to provide a very simple design. Each element does need to be configured independently. So we got to take a look at fault analysis and calculations and philosophies from the utility customers that we're working with to determine how we configure those relays to cover all those different fault scenarios. And look at how that coordinates with other equipment protection beyond the end of the line. So this is probably a pretty good place to stop if there's any questions. Any general topics on protection topics or kind of anything we've covered so far, or any other questions you have?
In 4 minutes, can you talk about the question I asked at the beginning, or is that better to do later on?
So I do have something on that. So your question had to do with, you know, what happens if you leave your grounds on transmission line and then energize it?
Right.
Yeah, so on that previous slide, I don't think they showed it on here. Let's see it. One thing is both of these protection elements I have highlighted here, pretty typical transmission line protection. The directionality piece of your directional overcurrent generally uses a voltage to provide that directionality. It uses the voltage as a reference compared to the current to say, is the current flowing towards the line, or is the current flowing away from the line? And similarly, your distance elements are going to use voltage to calculate the measured impedance at the relay. So in both cases, if that's what you've applied for line protection, your relay really needs this voltage to make an informed decision about if there's a fault or not. You know, the algorithm's going to need that voltage. And if you took this line out of service and grounded out the three-phase conductors here, because you had people doing work on the line, and that'd be typical safety procedure, would be you'd isolate it through a switch or an open disconnect. You'd open your breakers and you'd apply grounds to both ends of the line to provide safety for the workers that are going up there and replacing insulators or doing things like that. So, you know, Paul's question of what happens if you then forget to take the grounds off and close a breaker to try to energize the line. Well, if you've still got the grounds on this end, you've now created a line fault that is right at this terminal of the line, and you've got all three phases tied to ground. So you're going to see a whole lot of current, but you have now also grounded out the primary side of these line VTs. So you're never going to see any voltage come here. So your directional element isn't going to be able to make a directional decision, and your distance element isn't going to be able to calculate impedance. So you got to come up with a scheme to protect for that case. So there's a specialized scheme. It's more of a logical scheme that someone developed. It's been around for a long time, and it's been used pretty regularly for a case where you do have line side connected VTs, because the relay could also be measuring bus voltage, because there's really not an electrical difference between those voltages really. But if you get the line side VTs, it's called switch on to fault. And your switch on to fault protection, when your breaker closes, it's enabled for a very short amount of time, set amount of time to trip in that exact scenario that you've left your grounds on. And it would be set with just a simple phase over current element that would trip the line back off if, when you close the breaker, it switches onto a fault and there's a fault there. So it would very quickly, with no delay, would trip the breaker off to isolate the system again. And it's really there just to cover the case where your VTs don't energize, so you never get the signal that you need for you know, the other relay elements to operate. The problem with it is it's also load responsive. So if it's going to see normal load current as well. So you really don't want that protection to be on 100% of the time, and that's where the logic of the scheme comes in. That you close the breaker, it's enabled for a short amount of time. Once the voltage comes up on the VTs, you disable it, and then the rest of your protection is at that point now working, and will be able to provide that. And even if it does get a fault in that same location, the relay has a reference from the previous measured voltages that it can use as a memory voltage that it uses. So, in a normal operation, if you had a 3-phase fault show up right at those VTs, you're still covered in that case. You can still use the directional overcurrent or ground or phase or ground distance elements.
Great, thank you. Any other questions for our first night on distance protection with Mr. Davies? Okay, thanks everyone. Have a great weekend and we'll see you back here on Tuesday. Take care.
All right. Well, thanks everybody.
Thanks, Brandon.
Thank you very much.